This is Chapter 4, your introduction to hypothesis testing. Now we're getting into the crux of our content. So I pulled this text out of your textbook, and I'm going to read it to you. This chapter focuses on the basic logic for analyzing results of a research study. And then they continue on to tell you all of this general information about what the chapter does. And then we come to the second paragraph of the introduction to your chapter, which is where I want to focus. Many students find the most difficult part of the course to be mastering the basic logic of this chapter and the next two. This chapter in particular requires some mental gymnastics. Even if you follow everything the first time through, you'll be wise to review the chapter thoroughly. Hypothesis testing involves grasping ideas that make little sense covered separately. So in this chapter, you need several new ideas all at once. However, once you understand the material in this chapter and the two that follow, your mind will be used to this sort of thing, and the rest of the course should seem easier. So this is the main point I wanted to make. This is a challenging chapter. This isn't the chapter to daydream during course or to half read. This is the chapter to really work your mind hard. So pay attention during this chapter. So let's start with this explanatory example called Smart Baby. A large research project lasting many years has been giving babies this particular vitamin. And then the researchers watch their development for the first few years of life. So far, there is no evidence that it makes a difference. They don't find that this vitamin matters, right? Vitamin doesn't matter. Babies in this study walk at an average, remember that mu symbol, an average of mu equals 14 months, standard deviation equals 3, and it's normally distributed. So that's what they found so far. There's all those babies, there's the vitamin. But one researcher thinks that if they just refine this vitamin a little bit, it could make a difference. But the process of refining the vitamin is really pricey, so they want to see if it's likely to work before they invest a lot of money in it. They give this refined vitamin to just one baby, Eddie, and then they follow Eddie's progress. So this baby got this refined vitamin. So what the researchers actually want to do once Eddie learns to walk is to compare Eddie's walking age. Let's make Eddie in this reddish color. Compare Eddie's walking age to the age of babies in general, which they learned from their first study. So you'll recall that the average is 14 months. So let's put the average here. And that the standard deviation is 3. So we'll add the 3 to get 17 months, add the 3 to get 20 months, add the 3 to get 23 months, and going in the other direction, we'll subtract the 3 to get 11 months, subtract again to get 8 months, and again to get 5 months. These numbers are referring to the months of age infants first walked in the general population that they were measuring. This isn't saying that this is a typical, these are not typical ages necessarily for people in general. These are made up data. So that's what that represents. And of course, these are the raw scores and these are the z-scores up above. So what we're going to do is find out Eddie's walking age and compare it to what we know about this distribution. So in order to know if the vitamin really made a difference and is worth investing in, we have to understand how to actually test this hypothesis. And the first thing we're going to do is tease out the core logic of hypothesis testing, which relates to a legal tenet that we at least try to abide by in this country, although I fully realize that our efforts very often fail. But this is a legal tenet that underlies our legal system, and it is innocent until proven guilty. Unless we have sound evidence that someone is guilty of a crime, we assume they're innocent and we don't commit them to jail. To read what it says up here, if an individual is suspected of committing a crime, the tenets of our justice system declare that we approach the situation with the assumption that the person is innocent, and then gather evidence to show that she's guilty. This is designed to protect the individual from biased judgments about him or her or against him or her. We always assume the person is innocent, and that's the way it should work. So likewise, if a scientist thinks that a medicine will be effective in treating some condition or making people healthier, the scientist has to start with the assumption that the medicine makes no difference at all. Just like in the legal system, we assume that the person is innocent, so does the scientist assume that the medicine is ineffective. That protects the scientist from his or her own bias in judging whether or not it is effective. So the scientist, no matter what he might wish for in terms of having discovered a good medicine, the scientist will always start with the idea that the medicine is ineffective and will only cross this out if there's sound evidence that it is effective. So isn't that weird, right? Innocent until proven guilty, the same as ineffective until proven effective. So we call this the assumption of innocence in the legal system, or the assumption of ineffectiveness in a scientific study, the null hypothesis. Null means empty, zero. It means there's no difference, nothing's going on. So we might begin thinking about this by thinking about what the scientist who has the medicine or the scientist who thought that the refined vitamin would be helpful. The research hypothesis would be this prediction. The scientist predicts that an infant who takes the refined vitamin will walk earlier than infants in general. So this is not the null hypothesis. This is the research hypothesis. This is what the scientist is researching and what they are kind of hoping there will be some evidence to support. Just like the prosecutor is trying to assumes the suspect is innocent, but the prosecutor tries to find evidence that the suspect is guilty. So that's the parallel. So in a statistical hypothesis then, the scientist starts with a null hypothesis. And all that is an empty hypothesis that predicts no difference. Usually we shorten it to just write HO, like this O meaning a zero, the null hypothesis, the empty hypothesis. And the null hypothesis, in contrast to what we just looked at, would read an infant who takes the refined vitamin will not walk earlier than infants in general. So this is where the scientist begins and then looks for evidence. And so the alternate hypothesis is the same as the research hypothesis, and it's just the alternate to the null, the one that if we get evidence will support it. And here it is repeated. An infant who takes the refined vitamin will walk earlier than infants in general. So you'll see that these two hypotheses, the null and the research hypotheses, are identical. So this is the null hypothesis, the empty hypothesis. This is the research hypothesis. And you'll see that the only difference lies in the region of what the outcome is going to be. In the case of the null hypothesis, the prediction is that the infant will not walk earlier than infants in general, will not walk earlier, and here we just have will walk earlier. That's the only difference in those two statements. So now let's move on. Earlier we shaped this distribution and laid out exactly where the information from the norm is. So we looked at the months of age of walking for the general population. We wrote in those X scores. We had 14 months, 17 months, 20 months, 23 months, 11 months, 8 months, and 5 months. And we said we would compare Eddie's score to the normal distribution. And so now we're going to think about what we know about the percentiles. And we're going to fill in this statement. The majority of infants, 98%, will walk between blank months of age and blank months of age. If Eddie is like most infants, he'll walk somewhere in that range. So let's get our 98% marked in here. I'm going to choose a black pen to fill in this information. So you'll recall that 34% of scores are going to fall here approximately, and another 34% here. We know that 14% between 1 and 2 standard deviations, and between -1 and -2. And we know that 2% are going to fall in the tail. So that's the approximation. So we're asked 98%. So 98th percentile would be right here. We would take the 100%, that is this distribution in total, 100%, minus the 2% in this upper tail, and we discover that 98% encompasses all of this entire region. We could verify that by adding up what we know, by adding up the 50% that is here, and adding the 34 and the 14, and that confirms that 98% of the values are in this region. Let's go ahead and get the highlighter and highlight this region. So this is what we're looking for. We're saying the majority of infants will walk between how many months and how many months of age? Well, we can answer this question by just looking at all of these values. And we can say 98% will walk between 5 months and 20 months of age if we're looking at just that one tail. So let's go ahead and fill in the blanks. Let me get my pen out again. So here we go. We'll say the majority of infants will walk between 5 months of age and 20 months of age. And all I did is I followed these distributions down. What would be the odds then of a baby walking at 8 months? So if we look at that question, we would say, what are the odds of a baby walking at 8 months? Well, we would say that there is that 2% of the infants will walk at 8 months of age. Okay, so 2% walk, 2%, or there's a 2% chance that he will walk at 8 months of age. So in hypothesis testing, what we do is we look to see whether the scores earned by our individual, I'm putting this in parentheses, don't worry about this word too much right now, falls in the range where most individuals fall. That's all we're looking for. If the score is in that common range, like in the case of Eddie, if the score is in this, this range right in here, then we say we fail to reject the null hypothesis. So we don't reject the null hypothesis. The researcher is sad. There's not a significant result. We are saying in the end, our special person is no different than the general population. If the score is in one of the tails of the distribution, we reject the null hypothesis and conclude that our individual is different from the general population. We call it a significant result. So we might say it another way and say that if our individual has a score that's way out here in this tail, well, there's only a 2% chance of getting in that tail. Or if it's way out here in this tail, Well, again, there's only a 2% chance of getting a score in that tail. And we know that we have a 96% chance of getting a score in this middle region. And so depending on what we think is going to be meaningful, we would call this center region the reject region, meaning that if our participants' score falls in this region, we fail. This is the fail region. We fail to reject the null hypothesis. This is the fail region. This is the sad region. Our individual, our special individual, is just like anyone else. There's a 96% chance that they're going to fall in this region. But if a person falls in one of the tails, then this is the reject region. We have two reject regions in this example. We reject the null hypothesis, which says there's no difference, and we conclude that this treatment did in fact make a difference. So we'll be looking at lots of examples. Don't worry if you're not understanding this too much yet. This is the fail region. What it means is we fail to reject the null hypothesis. It means that the scientist is unhappy, usually because the result is not significant. If the score falls in the tail, then this is the reject region. Rejection makes scientists happy. They're weird. They like rejection. And this is a significant result. And this is a significant result. So we're going to work with this a lot, but the terms that you should know from this is, first off, the research hypothesis, which we're calling H1. And that's the hypothesis that the researcher puts forward based on his scientific understanding, such as the treatment will be effective. That's what the scientist usually wants to be supported. The null hypothesis is the empty hypothesis that states that there's no difference. It's like scientists, no, your idea is nothing. It's not going to work. There's going to be no difference. And we use this to reduce bias by assuming that the null hypothesis is true until we find evidence otherwise. And then the alternate hypothesis is the same as this. And I'm introducing both of these terms, alternate hypothesis and research hypothesis, because when you get to your research methods class, you'll see these used a little bit differently. Usually they use this HA instead of this H1. So I introduce both terms to you. Either one is okay. And then statistically significant is the last term, and it just means that the result obtained by the treatment group is unlikely to have been obtained in a sample drawn at random. And the treatment group could be Eddie with his special vitamin. It could be people taking a particular medicine or going through a particular type of therapy. That's what we mean by the treatment group. And when we say it wasn't likely to be obtained in a sample drawn at random, it means what are the odds that someone would get this score based on what we knew about the population. So we'll close with a quick little example problem. We're not even doing an example exactly, but your first practice asks you to decide whether you're dealing with a null hypothesis or a research hypothesis. And in both situations, we're comparing two different populations. So how to tell if it's the null hypothesis? Look for words like no different than, or no difference between the two groups, or group A is no greater than group B, or some other term indicating that these two populations are the same. That's what the null hypothesis means, no difference. In HA, or the research hypothesis, or the alternate hypothesis, we're going to look for words like this. More. The treatment group has more of something than the general population. Or greater. The treatment will have greater scores than the population. Or maybe it'll be the other way, less. The treatment group will have less or fewer symptoms of anxiety than the general population. Any term that says these two groups are going to be different is what you're looking for to tell if it is a research hypothesis. So we'll work with that in class, and we'll be working with these messy concepts this week and throughout the term.